Welcome back to the Explainer. So today, we are shattering a few illusions. You know that classic joke about physicists? The one where they try to predict the winner of a horse race by assuming all the horses are perfectly spherical and moving in a frictionless vacuum? Well, for a long time, that's kind of exactly how we've been taught to look at the world. We build these pristine, idealized models, massless strings, perfectly tiny point masses, zero friction, mostly because they make the math clean and easy. But today, we are leaving that pristine vacuum behind us. We're stepping right into the messy, chaotic, and honestly, incredibly fascinating reality of real physical systems. Okay, let's dive into this, because this is where the real fun begins. What actually happens when our perfect, theoretical textbook pendulum leaves the page and enters the real world? Well, suddenly, it has a shape, it has actual size, its mass is spread out all over the place, and as it swings, it starts bumping into trillions of tiny air molecules. It experiences drag. In short, reality just breaks our simple models. But, as you'll see today, physics isn't broken by reality. It just demands a much more brilliant, sophisticated approach. Here is our roadmap for today's explainer. Number 1, beyond the point mass. Number 2, the drag of reality. Number 3, 3 shades of damping. Number 4, measuring energy loss. And finally, number 5, forced oscillations and resonance. All right, let's kick things off with section 1, beyond the point mass, mass distribution. So our first major complication involves shattering that whole point mass illusion. In an idealized world, all of an object's mass is magically squished into a single, infinitely small dot. Because all the mass is concentrated right there, a simple pendulum's period, meaning how long it takes to swing back and forth, only really depends on the length of the string and gravity. The mass itself actually just cancels out of the equation entirely. But real objects? Think about a swinging metal rod, a wooden disc, or a heavy grandfather clock pendulum. They have their mass distributed all throughout a complex shape. This completely changes how the object resists angular acceleration, a property physicists call the moment of inertia. Plus, it changes the restoring torque provided by gravity, because gravity is acting on the object's center of mass, which could literally be anywhere relative to where it's pivoting. To actually calculate the movement of one of these physical pendulums, we can't just measure a string anymore. We have to know exactly how hard it is to rotate this weirdly shaped object around its specific pivot point. Enter the parallel axis theorem, sometimes called the Steiner theorem. This is just a brilliant mathematical tool. It essentially tells us that to find the moment of inertia around our new pivot, we simply take the object's existing moment of inertia around its own center of mass, and then we add the object's total mass multiplied by the square of the distance to that new pivot. It beautifully bridges the gap between the object's innate shape and how we've practically chosen to swing it. Now, what's really interesting about this slide is the final equation we get for the period of a physical pendulum. Capital T, the period, equals 2 pi times the square root of the moment of inertia divided by the mass times gravity times the distance from the pivot to the center of mass. I know, it looks a bit intimidating compared to the simple pendulum formula. But check this out. If you take this complex physical pendulum and mathematically shrink its shape down so that all its mass is just a tiny point at the end of a string, the moment of inertia becomes just mass times length squared. The masses cancel out, the lengths cancel out, and this big complex equation magically collapses right back into the simple pendulum formula. Even cooler, this physical pendulum math reveals a brilliant practical application, the reversible pendulum. Because of how the math shakes out, there are these things called conjugate points on the pendulum. If you physically swap the pivot point with the center of oscillation, the period of the swing remains exactly the same, no change at all. Engineers actually use this unique, reversible property to measure gravitational acceleration with absolutely unprecedented precision. Moving right along to section 2, the drag of reality, damped oscillations. Remember how we said real systems bump into things? Every time our pendulum moves, it's literally shoving air molecules out of its way. It experiences a drag force. For relatively slow-moving objects, this drag force is directly proportional to the velocity of the object, but acting in the exact opposite direction. The simple formula is F equals negative B times V, where B is just our damping coefficient. With every single swing, this velocity-dependent drag force acts like a tiny relentless tax, quietly robbing the system of its initial mechanical energy. And that brings us to a somewhat harsh truth, perfectly summarized by this quote straight from our MIT physics source text. The total mechanical energy of a pendulum is not actually conserved. Now, in introductory physics, energy conservation is sacred, right? But in the messy reality of damped oscillations, mechanical energy actively dissipates. It turns into heat. The energy isn't destroyed, of course, that would violate the laws of the universe, but it definitely leaves our pendulum. The physics isn't broken here, it just demands that our models evolve to account for this constant, inevitable energy drain. Which leads us to section 3, 3 shades of damping, categorizing the mess. So how does this energy loss actually physically manifest? Does the pendulum stop instantly, or does it slowly die down over an hour? Well, nature categorizes this whole mess into 3 very distinct regimes, depending entirely on how strong that drag force is compared to the natural restoring force. First up, we have the underdamped system. Here, the restoring force is way stronger than the drag. The system still swings back and forth, but the amplitude just gets smaller and smaller each time. Second, critically damped. This is the absolute mathematical sweet spot where the system returns to its resting equilibrium state in the shortest time possible without ever crossing that middle line to swing the other way. Finally, overdamped. Here, the drag force completely takes over. Think of trying to swing a pendulum while it's submerged underwater. It slowly, sluggishly oozes back to equilibrium without oscillating even once. And this brilliantly illustrates the difference. An overdamped system slowly creeps toward the zero line. That's like a heavy mechanical door closer, the kind that prevents a door from slamming but takes a frustrating 10 seconds to finally click shut. Contrast that with the critically damped system, which drops to zero incredibly fast, but notably, just like the overdamped one, never crosses the line. This is exactly how the shock absorbers in your car are engineered. When you hit a speed bump, you want the car to return to a smooth, flat ride immediately, without bouncing up and down like a pogo stick, right? Most systems we think of as regular oscillators, however, are firmly underdamped. Look at the classic sine wave of a pendulum swinging, but notice how it's bounded by an invisible exponential decay envelope. With every passing second, the amplitude is continuously shrinking. The system is just slowly bleeding out its energy. And that brings us to section 4, measuring energy loss, the math of decay. We know the energy is leaving, but physicists can't just say it's slowing down. We need to measure exactly how quickly it happens. We need to quantify the decay. One really elegant way to measure this is through a concept called the logarithmic decrement. Imagine measuring the maximum height of one swing and then the height of the very next swing. The logarithmic decrement is simply the natural logarithm of the ratio of those 2 successive amplitudes. What's absolutely amazing here is that for any given system, this number is a strict constant. It's inversely proportional to the number of swings it takes for the amplitude to decrease by a factor of e, Euler's mathematical constant. It is practically a precise fingerprint showing exactly how rapidly a specific system dissipates its energy. But perhaps an even more common way engineers talk about this is with something called the quality factor, or Q factor. The Q factor represents the ratio of the energy stored in the system to the energy dissipated per single radian of oscillation. It's just a pure number. So a tuning fork is very lightly damped. It loses very little energy per vibration, so it has a really high Q factor and rings for a long time. A guitar string is moderately damped, giving it a medium Q. And that car shock absorber we talked about earlier, it's heavily damped, intentionally engineered to have a very low Q factor, so it literally stops those oscillations dead in their tracks. Let's move to this next visual and see how this builds. A massive Q factor of 300 means the wave barely changes height. The energy decay is incredibly, almost painfully slow. As we drop down to a Q of 10, the decay becomes really obvious, and at a Q of just 3, the energy completely falls off a cliff. The math of the Q factor directly dictates the physical survival of that oscillation. Finally, we arrive at section 5, forced oscillations and resonance. So, if all real systems have damping and all real systems lose energy over time, how the heck do we keep a grandfather clock ticking indefinitely? So the crucial point is this. To keep a damped system alive, you have to actively feed it energy. You apply an external, periodic force that does positive work, exactly compensating for the energy lost to drag. We call this a forced oscillation. It's just like pushing a kid on a playground swing. If you push at totally random times, you just jolt them around awkwardly. But if you sync your pushes perfectly with the swing's natural frequency, you achieve perfect resonance. The amplitude builds and builds. If the swing has low damping, meaning very little friction, matching that natural frequency will cause a massive, sharp spike in amplitude. The swing goes higher and higher. But if the damping is high, that resonance peak gets much lower and broader. And that leads us to the ultimate real-world dilemma. Damping is constantly trying to bleed energy out of a system and bring it to a grinding halt. Resonance, on the other hand, can pump energy in so effectively that it builds to catastrophic levels, like a windstorm, perfectly matching the natural sway of a massive suspension bridge, causing it to literally tear itself apart. So I want to leave you with this thought. If damping destroys energy and resonance builds it infinitely, how do engineers perfectly balance these exact Q factors and force oscillations in our skyscrapers and bridges to keep them from collapsing? It is an incredibly high-stakes balancing act of physics, playing out all around us every single day. Thanks for joining me on this explainer. I really hope this helped clear up the messy, beautiful reality of physics. See you next time.